Alright, this recording is for cisp440 regarding the final exam. This is the last question, 5 out of 5. The interesting thing about this question is it was actually somewhat intended to help with question number 4, because by investigating this question, it might actually show certain important aspects of the algorithm. So you can answer question number 4. Whether that worked out or not, that's a different question. All right, so let's go ahead and get into this one. And I'm going to change my highlighter. Okay, the A-star algorithm can revisit edges even if the heuristic value are non-negative and do not overestimate, and that the distance of edges are also non-negative. So that means we are playing by all the rules that we have assumed when we work with the A-star algorithm, and yet we can still revisit not only vertices but edges. Show a graph, define the start and destination vertices, define the distances of edges, define the heuristic value, so that the A-star algorithm will revisit at least one edge. This means the same edge is considered more than once in the execution of the algorithm. And to be more specific, on line 13 in listing 1. So let's go back to line that particular line first, because it is important to understand what we are talking about. So this time we're talking about line 13, which is this part here. So we are basically revisiting the edge in the for each. Okay. Now, whether that edge is a part of the solution graph, the question did not say. It just says we are reconsidering that edge. We're touching that edge again on line 13 of that listing. And there's a big hint here. You can come up with your own graph, but this is a simple one that works. In other words, this is one of the minimalist graph where something like that is going to work. So the hint is, you might want to go with this first, okay, and see whether it works, because it only has 4 vertices, because the vertices is this particular set here, and this set over here is the set of all the edges. So that's how a graph is represented. Okay, all right, so let's go ahead and just draw that graph and see what happens. I'm going to draw the graph over here. So and also, if you read the documentation, or if you read the text here, it also says, make M the start vertex, Q the destination. So let's do it here. So we got M as the start vertex, and then we got Q all the way here as our destination. So M goes to P. Okay, so M goes to P like that. M goes to R. So M goes to 2 different vertices like that. R goes to P, and then P goes to Q. So this is the topology of the graph, but you have to come up with the cost of the edges as well as the heuristic values, so that an edge is visited more than once. Okay, so where do we start here? So the question is, which edge do you think is going to be revisited more than once? The initial edges, the edges leading out from the start vertex, MP and also MR, are very unlikely to be revisited, because any revisit has to be triggered by an element being selected from the set O, and we know that M cannot be reintroduced into the set O, because M is a start vertex where it has its own G value initialized to 0, and that can never be getting any smaller. And as a result, we know that the edge MP and MR cannot be of consideration here. The edge RP is also unlikely to be revisited, because revisiting means the vertex I should say the tail of that particular edge, which is R in this case, is getting put into the set O more than once. But in this case, there are no alternative paths to go to R, so there's no way that it can be reconsidered. So that means the edge that's going to be revisited is going to be PQ. That's going to be the edge that we want to revisit. Okay. So so now we have to assign weights to these vertices. So the key is we get to we go from M to P, and then P would look really good, so we have to expand it instead of we okay, we first start with M, we put P and R into the set O, and we will pick P over R, and then P is going to lead to Q, and that completes one path. But the G value is going to be greater than at least one of the F values, so that will force us to go back and revisit one of the edges, and that will lead to P again, and then P, because this time it has a lower value, it'll be put into the set again and be revisited, and as a result the edge PQ is going to be expanded again in the algorithm. Okay, so in this case the weight of the edges is not as important as the heuristic itself. Okay, so we can basically, out of the two paths from M to P, which is the single edge, versus the other one, we have to make it so that the single edge is the one that is going to cost us more, but the heuristic is going to favor P instead of R when we have both of those in the set O. Okay, so let me write down that requirement. So what we want is to make sure that f of R is greater than f of P. That is one requirement in order for us to favor P instead of R and then pick it out of the set O, because when you pick something out of O, you have to explore all the outgoing edges. So we want that to happen. But at the same time, we want the length of the path MRQ to be less than length of MR. I forgot one thing here. MRPQ instead of MPQ. MPQ. So these two are basically the constraints that we need in order for PQ to be revisited. Okay, so given that, how do we make that happen? So we'll go with, let's see here. I'm just trying to so we want these two to be, we want 1 over here, a 3 over here, and then this one doesn't really matter because it is a common edge for both of these paths from M to Q. So the cost of PQ as an edge can be anything. Let's make that 2. Okay, so the key is the H values. We want to make sure that R doesn't look as attractive as P when we get there. So what we want to do is to say the H of PQ is going to be as small as possible because we want to make it attractive, and 0 is as attractive as it gets when it comes to heuristics. And then with the other one, which is R, we want to make it as unattractive as possible, which means we want to maximize it. Maximizing a heuristic value means it is really just the actual length of the path from R to Q in this case, which is exactly 3. So let's go ahead and check whether this is going to work or not. Because what this is going to do is by the time we compute the F value of P, So the f value of p is now going to be 3, which is the length from the start vertex to p, plus the heuristic, which is 0, which is going to be 3. The f value of r, on the other hand, is going to be 1, which is the g value of r at the time, plus 3, which is going to be 4. So this is going to force the algorithm to choose p instead of r when we get there. The heuristic value of m doesn't really matter, because that is not useful at all, because that's, it's not going to help us choose which alternative to go, after the start vertex. So that part doesn't really matter. We can make it 0, okay, just so that it's easy to figure out. And of course, there's also the last one, which is h of q to q, which is always 0, because it doesn't cost us anything to go from a vertex to itself. All right, so this is the part, most of the answer. The edge that is going to be revisited in this case is PQ. So we'll just have to say PQ is revisited. And that's it. So the main point, or the steps of getting this done, is first to identify the constraints. Okay, first step is to make the graph, okay, so that you can understand that certain edges cannot be revisited, like MP and MR cannot be revisited just because they come from the start vertex itself. And then RP cannot be revisited because the G value of R, once it is set, once it's determined, or changed from infinity to 1 in this case, it's not going to change again. So the only edge that is going to be revisited is PQ. That leads us to step number 2, which is, well, in order for the edge PQ to be reconsidered, we need to make sure that the algorithm chooses P instead of R when both of them are in O, which means, the F value of R has to be greater than the F value of P. So when we choose, we're going to choose P instead of R. But in reality, we want to make sure that the length of MRPQ, MRPQ, is going to be less than the length from M to P to Q. So this way, the G value, the first time we get to Q, the G value of Q is going to be 5. And 5 is still going to be greater than 4. And that means the algorithm cannot terminate because of the additional condition yet. It has to consider R in the set O, because f of R has a value that is less than G of Q, and that is the other key. So given number 2, these constraints here, we can now work out the values, the cost of the edges, to make sure that the length is, so the length here is going to help us determine the values of the cost of the edges here. And then based on that, the f value, okay, this is going to look really bad, so let's change color. So the extra constraint, f of r is greater than f of p, is a matter of defining the heuristics. So that leads to the determination of the heuristics. One is the minimum, as attractive as it gets as a heuristic. The other one is as large as it gets, which means it is as unattractive as it gets. Okay, and once we have that, that's pretty much the whole thing. The other two heuristic values are really, they just have to be there so that the A-star algorithm can run. But what value we choose doesn't really matter as long as they're legitimate. And then of course, that's the last part here, which so this is 2, this is 3, this is step 4, and this is step 5. At least that's what is going through my mind when I work on this particular problem. All right, well, that's the last one. I'm going to grade it very soon, and I'll be assigning points. This one is not as difficult to grade as number 4. 4 was really, really hard to grade. This one is a little bit easier because I can just check whether um, an edge is going to be revisited based on the constraints. So number 2 is really the key to this entire question. It's identifying these constraints here. So there has to be 2 different paths, and one path has to look more attractive than the other path at one point, but the 2 paths also must share a single common, at least one single common edge, so that that edge is revisited again. All right, so I'm gonna write down the rubrics and then start grading. And have a happy new year. I'm kind of glad that I can almost get all the final exams done before New Year Day. And let me get to OBS.